And we're live. Welcome everyone to the Hedera Technical Community Call for the month of May. I'm your host, Ed Marquez, leading developer relations at Hashgraph. And today we have an outstanding set of speakers and a very interesting topic. We're going to dig deep into the TSS ceremony, which is a significant cryptographic development on Hedera in 2026. And you can think of it as a one-time setup that upgrades the network going forward. So we're going to hear from a few Hashgraph colleagues, including Joseph Sinclair, who is a principal software engineer. Also from Rohit Sinha, who is the head of cryptography at Hashgraph. Now, before we hear from these folks, I do want to set the framing, about this TSS ceremony and the downstream implications by welcoming our VP of Engineering at Hashgraph, Richard Bair. Welcome, Richard.
I think I'm in. There we go. Hey, how are you doing this morning? Good to see you.
Good to see you too. Thank you for joining us. So I know we have you only for a few minutes today. So what can you tell us at a high level about the TSS ceremony, to set the stage for our presenters that are going to take us on the deep dive in a few moments here?
Yeah, I think the first question that would come to mind if I were watching this was I'd say, what is TSS? Why is this important and what's the implications? And, we've been working on revamping our block structure for the last couple of years, and it's really good. The design of the system is top notch. It's the best that I've seen in crypto. Our blocks have some really great properties about your ability to prove things in them, including being able to create state proofs from them. And one of the key essential parts of that system is the signing mechanism that you use. So essentially what TSS is it's a special type of cryptographic signature that attests to the validity of the block using a combined signature of all the different consensus nodes on the system. So all the validators are combining their signatures into one signature that sits onto the system. Now, there are other chains that are doing something similar using a technology called BLS. Ours is the type of a BLS as well. But what makes ours really unique is that we added an additional feature, which is a recursive ZK proof that proves the set of signers going all the way back to the beginning. So in some other chains, what you'll find is that you have to maintain a knowledge of who was allowed to sign in order to produce a signature on these chains. But what's really powerful about the way that we've designed it is that you don't have to do that because we have the power of ZK proofs that we're using on every single, we carry forward on every single one of our blocks. And what this means is that if you have a block, you can independently verify that that block is correct. I like to say that even if you took the bytes of the block and you chiseled it into stone and you buried it in the earth and someone dug it out of the earth 1,000,000 years from now, they'd be able to take those bytes and they'd be able to run the cryptographic proof and they would say, by golly, 1,000,000 years ago, this Hedera network produced this block. And it would be something that you could rely on with math and nothing else. So I think it's super exciting. We're definitely upgrading our blocks in our blockchain, and the TSS is an essential part of that. And the guys that you're going to hear from here in a few minutes, they know all the details.
That's amazing, Richard. Thank you for setting the stage. And with all the marketing and the awareness that we've had around Blockstream, block nodes, a very common question that we now get is the Hashgraph consensus a DAG or now a blockchain? So what would you say to those folks? How would you address that question?
Yeah, that's a great question. And I know that there's confusion about that because, history being what it is, the reality is that we are not making any changes to the consensus algorithm at all. Hashgraph algorithm is a directed acyclic graph, or a DAG, and it is the thing that is responsible for ordering all of the transactions. And the way that it orders the transactions is the way that we've always done it. And it's the best in the world. Like I'm always blown away. I'm like, everybody should be stealing this algorithm. It is the best way to order transactions. It's totally fair. It's totally secure. It's super fast. It meets all the criteria that you could want. It's a great algorithm. We continue to use that algorithm for ordering the transactions. The blockchain itself is the historical record of all the transactions in the order that the Hashgraph produced them in. So you can think of the Hashgraph as being this magical machine. A bunch of random transactions come into it, an ordered set of transactions come out of it. We execute those transactions, And then the list of transactions and all of their effects are bundled up in these blocks, with each block having a cryptographic hash of the previous block, forming a chain of blocks, and each one of them having a distinct signature on them that makes it so that you can trust that block, knowing that it was produced by the consensus nodes. We've actually had this system, an analogous system, from the beginning. Instead of calling them blocks, we called them record files. Instead of calling it a block stream, we called it a record stream. And what we found was that was just kind of confusing to people, because they kept getting this confused as to, are we a DAG, or are we a blockchain? It's like, well, we've always had a blockchain. It's just that we called it a record stream with a bunch of record files. And the signatures were these separate files that you had to download, and it was kind of cumbersome. So what we've done is we've upgraded all of that and adopted terminology that everybody will understand, that, this is just a cryptographic series of blocks. And, Ethereum has one method for deciding what the consensus order is. Algorand has a different method for deciding consensus order. Hedera has a different method for deciding consensus order. However you order those transactions, they all find themselves in a block at the end of the day.
Excellent.
So that's what I would say. I'd say,
yeah, that's a spot on and a great clarification. Now, you mentioned it's the best in class consensus algorithm. People should be stealing it. The good news is that it's totally open source under the Linux Foundation Decentralized Trust, or LFDT. What can you share with us around Hyro and how people can get involved with the Hyro project?
Yeah, so for those who are not aware, all of the code that we have for Hedera is open sourced under the Linux Foundation. The parent project is called LFDT, and within that is our Hyro project. And you can go to our website, and it's spelled Hiero. And sometimes people pronounce it hero, but it's actually Hyro, as in hieroglyphic Hyro. And so it's got a little Egyptian hieroglyphic, sort of a glyph going with it, a little symbol. But yeah, no, it's open source. All of the stuff is open source. The consensus nodes, the block nodes, everything that you're going to see today that the team has been working on is all open source. And the important thing about it being inside the Linux Foundation is that is a vendor neutral organization, meaning that even though the code is there and there's a lot of people from Hashgraph who participate on it, anybody else can participate on it as well. And the number of contributors that we've had have just been growing. A lot of participation around the SDKs, for example, have just been phenomenal. Some of the SDKs are completely community led, and those are actually some of the more vibrant projects in the entire in all of Hyro. So we definitely encourage people to come check it out, star the project, like it, clone it, fork it, experiment with it. And, we'd love to have your participation on the project.
Absolutely. That's a great call to action for today's call. So go check out Hyro at hyro.org, folks, and the GitHub repositories. So, Richard, I do want to thank you for being here with us today, setting the stage for our presenters. And we're looking forward to welcoming you in the future sometime.
Sounds good. Thanks, Ed. And you guys have got the best people on coming up, so they're going to be able to tell you everything you want to know.
Absolutely. Thank you.
Yeah.
All right, coming up next, we're going to welcome to the stage Joseph Sinclair, principal software engineer at Hashgraph. And he's going to tell us more about the TSS ceremony, what happened, and all the details on that. Hey, Joseph, welcome.
Hey, Ed. Good to be on here.
Thank you, Joseph. Before you do the deep dive, would you mind telling us a little bit about your role and then what you do day to day, maybe the HIPs that you've contributed to, and then I'll let you jump into the deep dive for what happened around TSS ceremony.
Sure. So my role at Hashgraph is, as you mentioned, principal software engineer. I work primarily these days on the block node, which is a system that will manage the block stream as we perform that upgrade. I also work on some of the HIP documentation, across different teams, including HIP 1398 for the TSS ceremony, which is what we're discussing today. Some input to HIP 1200, mostly just editing there. Rohit's the genius behind HIP 1200, which describes the TSS cryptography, as well as 1056 for the block stream and 1081 for the block node and a bunch of others.
Excellent.
So I tend to cross a lot of different realms, but these days it's primarily the block node and the block stream.
Amazing. Thank you, Joseph. And that's a great segue for introducing Rohit, head of cryptography at Hashgraph. And, Rohit might look familiar to you folks from Hedera Dev Day, where he had an amazing fireside chat with Dr. Lehman Bair. But Rohit, please give us a quick intro.
Yeah, thanks, Ed. Yeah. As Joseph mentioned, we've been working heavily on TSS and various cryptography. I guess my role within the company is to work on all of our cryptography needs, but most of my time has been spent on TSS over the last year or two. But yeah, excited to talk about it. Yeah.
Amazing. All right, Joseph, it's all you. Take the mic and let us know what happened with TSS ceremony and give us all the details.
Sure. So in April 15th through 28th of this year, we ran a ceremony. This ceremony is basically a series of executions of specifically structured software. The software was operated on the physical hardware that operates the consensus nodes, as well as hardware provided by several community organizations. The ceremony is a modified Powers of Tau ceremony, which Rohit can explain in more detail, which was run by an orchestrator code, some software written in Java that the team deployed to the consensus nodes and provided to these community members. The orchestrator code received a large data file from S3 storage, transferred that locally, performed the cryptographic operations, and then transferred the results up to that same area of S3 storage. The process actually had several phases. So all of the nodes taking turns downloaded the data, performed the cryptography, uploaded their results. The next node in turn downloads that data, the results, does their cryptography, uploads their results, and so on throughout the consensus network, and then on through the community participants as well. We made sure the community participants were at the end so that they had the opportunity to ensure that the process was fair from their viewpoint. Then some additional cryptography was performed, and another set of data was uploaded to start the process a second pass, going through all of the consensus node and the community members a second time. The output of this ceremony is critical data, which was used to generate the wraps, proving, and verification keys. So these are the keys that they're public and they're available to anyone, but they're used to prove, to generate the ZK proof and to verify that ZK proof whenever seen. So the proving key helps to generate it, and then the verification key obviously helps you to verify it. Additionally, it provided some inputs to a circuit that helps to generate the RAS proof in an efficient manner so that it's not this massive giant blob of data, but it's something much more manageable. At the end, we produced a complete transcript where every machine signed its output, and all of the data and all of the transcripts are available online and can be viewed, so that anyone who chooses to and wishes to operate the necessary cryptography can verify that all the results are honest, or at least honest to the extent that they can be verified. We did learn a few interesting lessons from this event. The pardon me. The first phase of the event requires fairly substantial cryptography. It's not easy, and it requires quite a bit of CPU and memory overhead. Some of our nodes were not able to complete in a reasonable time frame. Now, we had done some testing and anticipated this, so the orchestration software cleanly managed. If a node was unable to complete, we simply skip that node and move on to the next one. That's still entirely secure because the cryptography system and the entire ceremony remains secure as long as at least one node is honest in its actions. So we don't need to worry about every single node participated in every single phase. We need to be sure that as many as possible so that we know for a fact that at least one of them was honest. Now, how do we know they were honest? Well, we wrote the software that performed the ceremony, and anyone who wishes to can verify that that software does not merely remove its toxic waste, the randomness that it's mixing into the data, but it never even stores it in the first place. It loads it, it generates it in memory, it performs its function, and then it removes the memory entirely. So there's no possibility of it storing that data, which is the critical element. We need to know for sure that that data is not stored anywhere. So that data, that software is open source. It is visible to anyone, and anyone who wishes to can verify that it does do what it's supposed to.
That's amazing. Thank you so much for that overview, Joseph. Any other points that you want to walk us through, or are those the majority of overviews and lessons you want to share today?
So the major lesson we learned is anytime you're running a ceremony like this, over-specify your hardware. We tried to be very efficient in specifying our hardware and didn't quite work out the way we wanted to. It worked out well enough, but not as well as we would have hoped. So anytime you're running a ceremony or function of this type, specify more hardware than you think you need, probably about twice as much as you think you need, and you'll probably work a lot better.
That's amazing. Absolutely. And thank you for sharing that. All right, folks, there you have it from Joseph. All the details around what happened, the dates from April 15th to April 28th, the behavior of the orchestrator code, and also the value of the transcripts and the verifiability that provides. And it's absolutely amazing to hear that there was community involvement for community projects, which you're going to hear from next week or in the next couple of weeks, as we're planning that session too, to bring some of those projects that contributed to the process and hear from them as well. All right, Joseph, thank you so much for joining us today. Next, we'll bring Rohit back to the stage, and he's going to give us how this works and why this works, and a lot more details around the cryptography and the whole process around TSS and the ceremony. So, Rohit, take it away.
Great. Yeah, as Joseph mentioned, terms like the wraps proving key and circuits, and I wanted to dive deeper into what exactly those are. And in fact, I'm going to spend a lot of time on why we have a ceremony rather than the ceremony itself, because Joseph did a great job describing the ceremony itself. But let's try to understand why we did the ceremony in the first place, where it all fits into the whole cryptography of TSS. And so bear with me, and I'm going to take small steps through this. So most of the slides are going to talk about TSS itself, but eventually I'll tie it all together with the ceremony. All right. Yeah, let's go in. So yeah, just to remind ourselves what TSS is trying to do is basically trying to provide verifiability of consensus data or the block data beyond the consensus nodes itself. So we should be able to verify a TSS signature without relying on any additional intermediary parties, like things like bridges, and that's pretty powerful. And the way we achieve this, and we're not the only ones to look at this problem. Other chains like Ethereum have also studied this problem. And the primitive that kind of fits very nicely in here is something called a threshold signature scheme. This is a cryptographic protocol that allows a bunch of parties to come together and produce a joint signature on a message. And there's a threshold access structure here, in that as long as any T out of N signers, and both T and N could be arbitrary, for example, 3 out of 5, 5 out of 9, whatever. As long as any T out of N signers agree to sign this message, you get a valid signature out. And what makes this interesting and also challenging to build is that the signature kind of looks like it's a single signature. Of course, you could have concatenated T signatures and call it a threshold signature. But the property that we really like about threshold signatures is that the size of the final signature is same as the size of a single signature, as if one node signed off on it. So there's this aggregation property that we really like. There are many threshold schemes, signature schemes in cryptography literature. We've been working on it for 20 years as a cryptography community. BLS is a very popular one, but there are other ones like Schnorr. And yeah, as we'll see later, we had to develop our own threshold signature scheme with some additional properties that these traditional schemes didn't satisfy. But we are based, we do build on top of BLS, and I'll get into that. So yeah, so where do the existing TSS schemes, like I mentioned, BLS, where do they fall short? So typically, once we have this block stream, we'll have a bunch of blocks, each with a TSS signature on it. However, periodically, we're going to have changes to our validator set. So for example, let's say once a day, the blocks or the nodes on our system may change, or their weights may change based on change in stake. And if we had to use one of these existing systems, like let's say threshold BLS scheme, you could use it, but the problem is that every time the set of nodes change, there's some kind of setup that you have to do, which outputs a verification key. That verification key is what you verify the signature against. But if you change your network or you change the weights, it's invariably the case that affects the verification key. And that means, as someone who's verifying these signatures, let's say it's another smart contract living somewhere else, or just someone else wanting to verify our TSS signatures on the blocks, they will have to always keep figuring out what is the latest address book, and when I say address book, I mean the set of validators and their weights and their public keys. What is the latest address book on the Hydro chain? And that's kind of inconvenient and messy to work with. So our threshold signature scheme has the following properties. We want to support, of course, evolving address books. But at any point in time, the TSS signature that we have is verifiable with respect to a fixed verification key. And we call that a ledger ID because this verification key is established when you create the ledger, let's say at Genesis, or at any point in time. It doesn't have to be Genesis, but at any point in time, you choose to establish what we call a ledger ID, which is a cryptographic description of that ledger. That establishes the fixed verification key. And no matter how the address book evolves in the future, you can always verify with respect to that, as Richard mentioned earlier in the call. The big requirement, and this is something that existing threshold signature schemes in cryptography do not support, is this native support for weights. All signers are not equal. So earlier when I said T out of N, that implies that any T out of N can sign. But for us, it's not just the count. It's actually the signers themselves may have different voting power or different weights in the threshold signing process, and we need to account for that. Of course, we want things to be efficient. It's no point developing something that's not efficient. Roughly, we see the signing time to be on the order of 20 milliseconds, which we think is good, fast enough. It must also be efficient to verify them. Again, we measure verification to be roughly on the order of 20 milliseconds. Seems reasonable. We want the signatures to be small. And in fact, interestingly, we made our signatures to be constant size. They're between 2 to 3 kilobytes. And no matter how the network evolves or how many nodes we have on the network, that size, that number is going to be fixed. And it's reasonably small in practice too. And finally, we do care about like the kind of cryptography you use. We want to use highly vetted cryptography. That's one. And we want to be able to also make it easy to swap things out in our entire system, which we have to do for post-quantum security. Okay, so let's dive into it. So the way we do TSS is we break it into two systems. One, as Joseph mentioned, called wraps, and the other is hints. The goal of hints is for at any point in time, if you want to sign a block, the set of nodes in the address book, and not all of them may be online, whoever is online, as long as you have half of the address book by weight, you get a valid signature on that block. And that's what hints does. It's a weighted threshold signature scheme. However, hints, the verification key does change as the address book changes. So let's say a day from now you change or you add a node or you change their weights, that does impact the hints verification key. But remember, we want to verify our TSS signature against a fixed verification key, and that's the job of wraps. This evolution of verification keys that are within the hints, that is tied all the way to the ledger ID, which makes, when you combine the two subsystems together, the entire TSS system has the property that all signatures are verified with respect to a fixed cryptographic material called the ledger ID. And that's what wraps does. It's a recursive proof that the latest address book is a descendant of the Genesis address book, or the cutover address book, what have you. Yeah. By the way, feel free to Ed, feel free to stop me if you see any questions showing up. So hints, I'm not going to talk about it because our goal today is to discuss the ceremony, which has to deal with the wraps portion. So I'm just going to mention in passing that if you want to find out more how hints works, feel free to check out the paper. We worked together with several academics, published it a couple of years back. And all hints does is construct a threshold signature that half of the address book by weight has signed off on that block. Okay, that's hints. But let's dive into wraps because that's what we care about, because we care about the TSS ceremony. And the goal of wraps is to prove this chain of evolution in the address book. So at any point in time, it proves that the latest address book is a descendant of the previous one, which is a descendant of the one before that, all the way down to Genesis or cutover. Okay. But before I do that, I want to give a brief overview of what snarks are. It's something I'm sure a lot of us have come across at some point in the space. But I won't get into the math, but I just want to give the intuition of what the primitive allows us to do, because we use this very heavily. We use something called recursive snark, but let's understand what a snark is first. It's a succinct proof that a certain statement is true. And as an example, let's say you computed a SHA-256 or a SHA-384 of some data, and the hash itself, you can prove, for instance, you can prove that you know the data that you hashed to get that you got to get the hash value. And the key requirement of snark, the S in snark means it's succinct, and what that means is that it is very fast to verify that the prover did indeed know the statement, that they did indeed know the witness, M in this case, that made the statement true. Of course, the trivial thing to do is to just, for example, in this case, give the message to the verifier and they can hash it, and of course, then you know. But what makes this interesting is that, well, if you did that, the verifier has to download the message, it has to compute the hash. The interesting thing here is that the verifier does compute. The verifier's work is sublinear in the computation itself. That's what makes it challenging to build, what makes it interesting to use in practice. Now, I wrote this in natural language, I know AM, but typically we express them in something called a circuit, which Joseph mentioned before. We describe the computation that we're proving as basically a circuit, which contains a bunch of additions and multiplications. And turns out you can express any computation as a bunch of adds and multiplies. So it's quite interesting. So if you look at the statement before, I can rewrite them in a more mathematical form that, hey, if you encode SHA-256 as an arithmetic circuit, and if you apply that on a message, you get a specific value hash. And if that is indeed the case, the circuit outputs a fixed value, let's say 0 or 1. And now the prover has to prove that, yes, it does indeed know in a message M that makes the circuit output 0. That's how you rise above the natural language and actually formally encode the semantics of the computation. As another example that actually is more relevant for us, you can prove that you know a signature. That let's say you know a valid ECDSA signature on a message M. And how do you do that? You actually encode a circuit that runs the signature verification algorithm. So if you prove that the signature verification succeeds, that means you did indeed know a valid signature. And that's I want you to remember that, because that's what we'll be using later. So So let me recap. The algorithms that we have in a snark are basically three algorithms. There's a setup phase that basically looks at the arithmetic circuit and gives us certain public parameters. If you recall, again, from Joseph's presentation, he mentioned wraps proving key. That's basically what the setup will give you. And once you have that polynomial, or as many times as you like, you can run a prover algorithm and correspondingly run a verifier algorithm, and you can prove things about the circuit that you have just preprocessed. Okay. Let's. I want you to remember this because we're going to come back to it when we finally discuss the ceremony. But the ceremony is a ceremony for wraps. So let's talk about what wraps actually is now that we know what snarks are. So again, the goal here, you have rotating address books, and we want to prove that it's this descendancy chain. And let's make some baby steps towards it. So, well, one option is a bunch of nodes. Well, how do we do that? How do we prove this descendancy chain? Well, you can have nodes on an existing address book bless the next address book. So folks on roster 1 blessed roster 2, and folks on roster 1 are blessed by roster 0, and so on. And if you take all of these signatures and present it to whoever is verifying the TSS signature, of course, this is valid. It works. They can check that. Look, yeah, there is this chain of signatures. But of course, as you can see, this is going to be very expensive. The verifiers has to do work that's both linear in the time. So a year from now, this is going to be like really unwieldy because you have 365 such address book transitions. And also it's linear in the number of nodes, right? On both dimensions, we have an issue. So let's try to fix that because we know how to do snarks. And snarks give us the succinctness property that a verifier can check a statement with much less work than what a prover has to do. So we can take a bunch of these signatures and slap a snark proof on it, saying that, hey, I know such a list of signatures exist. And if you take these snark proofs and give it to the verifier, now the verifier is doing a lot less work. It's not doing work linear in the number of nodes, only, I guess, linear in the time, because you have a snark proof for each address book. So we made progress. But of course, that's, again, not good enough, because it's a year from now, this is going to be a lot of proofs to verify. So finally, let's try to do a snark proof that covers all of these signatures for all of the address book transitions. We can feed it to one snark prover. Now, this works from the verifier's perspective. The verifier is only looking at one proof. But this is actually going to be really bad for the prover, because the prover has to work with a gigantic number of signatures every time we have an address book transition. So you can probably see where we're getting here. We're going towards recursion, where you don't do all of this proving all at once. You do it incrementally, which is where I'm going to quickly discuss the next primitive that we use. This is, again, something folks in cryptography have been doing a lot of interesting work in the last 5 years, and we are able to benefit from it. It's something called incrementally verifiable computation, and it uses something called, or it's implemented by something called recursive snarks, as folks mentioned. The goal here is pretty straightforward. Let's say you have a incremental computation where you do the same computation, let's say, several times, which is what we have. We have a chain of list of signatures. So it has that same structure in the computation. And you prove that starting from an initial state, you can get to a final state using a sequence of applications of this function. Basically, our computation, it can be modeled exactly like this. And that makes our job much easier. So at any time we rotate the address book from, let's say, nth address book to n+1, we take the previous snark proof that we have, or some, there are many ways to do recursion. There's one way to do black box recursion. There's another technique called folding. We use something called folding because that ends up being, allows us to do recursion very efficiently. But never mind those details. The point here is that based on something you computed yesterday, you do an incremental amount of work to produce the next snark proof. So every time you rotate the address book, you do a little bit of work. You don't do all of that work all at once. So that allows us to do things, keeps things pretty manageable. In our system, we spend about 5 minutes of compute time every time we rotate the address book. And if you rotate it not that often, let's say once a day, we can totally afford it. So with that, we're basically done. We have this recursive snark proof that allows us to prove that the latest hints metadata, hints verification key, is actually something that came from a descendant from the Genesis. Okay, and that's all that we're doing. And of course, these individual signatures, they're attesting to the hints verification key. But let's not get into that. So to verify the TSS signature, you have to verify both the wraps and the hints proof. You first verify the wraps proof. That gives you certainty that the hints verification key can be used for that address book. And then that specific block signature can be verified with respect to hints. That's how the two systems connect together. It's very decoupled, except for this tiny linkage. Okay, finally, this is the last slide. Well, this is where the TSS ceremony fits in. We've just looked at hints and wraps. TSS ceremony was about wraps. If you recall, a snark has three algorithms: a setup algorithm, which gives us these public parameters, and you use those public parameters to both generate proofs and to verify proofs. These parameters are dependent on the arithmetic circuit, which in our case is a very specific circuit that deals with these signatures, a chain of signatures that we saw. And the goal of our TSS ceremony was to, instead of having a trusted party that generates, so this pre-processing setup is an algorithm. You could ask one person to run it and give us these parameters. I could run it on my laptop, but how would you trust me? If I were malicious, I could have generated public parameters that allows me to later forge whatever proofs I want, steal all the money in the world. I don't want to be able to do that. So that's the reason we had the ceremony where we invited so many folks to participate with the property, and that as long as one of the parties involved in the ceremony is honest, we have full security. By the way, we did not invent this. This is stuff that we've known how to do for about 10 years now. Our circuit uses something called Groth16, which is a snark system. There are many established ways to do a ceremony for Groth16, and we did something that one of those techniques. So yeah, as Joseph mentioned, we have the ceremony where parties take turns participating. And the way you should think of this at a very high level is basically you're adding entropy. So every party takes turn adding some amount of randomness into this parameters. And the property of randomness is that if you have a bunch of parties contributing randomness, as long as one party contributed enough randomness and they were honest in that they did not hold on to the randomness, you get pure randomness in the full system. It's just like, think of it as the additive nature of the randomness, if you will, which is very nice. As long as one of the parties in this chain, they participated honestly, when I say they participated honestly, they basically supply entropy. And there's also a lightweight proof that they do that they did, they took the previous person's output and added entropy. That, for example, Charlie didn't skip over Bob, took Alice's input and added entropy. That would be bad because then Bob didn't get a chance to participate. So Charlie's proving that he took Bob's output and added some entropy that he knew that entropy, what that was, and then the result is sent over to David and so on. And we do 2 rounds of this protocol, and eventually what we get are the public parameters for TSS wraps. So that's it. That covers the whole thing. Happy to also take questions. But we're still working on this actively. The big next step for us is how to make all of this post-quantum secure. And that's a very active line of work for us.
Rohit, that was an amazing overview. Now, this first question that came from the community actually relates to that very last point on next steps and the future direction. So the question comes from Dave Proxy 80. Love these usernames. Does TSS push Hedera towards quantum resilience?
Yeah, as I mentioned, we're working on it. What I described today is not post-quantum secure. In fact, a lot of things are are not very structured and they're small because we use elliptic curve cryptography. So a big next step for us is to migrate both the hints and the wraps components towards post-quantum alternatives. But as of today, we don't have that. Yeah.
Excellent. Another question that came from Nick Altmaier. Hey, Nick, long-time community member here. Does the second parameter n mutate the resultant key length, or would any t out of n result in the same length / size of key? He did acknowledge that you addressed his question, but for the benefit of the audience, if you could go over that again, that would be helpful.
Sure. I imagine that's referring to a standard threshold signature scheme. So the way that works is you have a setup even for a threshold signature scheme. Sometimes you run a distributed key generation protocol where parties talk to each other and they get this. In hints, we use something called a silent setup. Whatever the situation is, the goal of a setup algorithm for a threshold signature scheme, again, not to confuse it with the snark setup, because that's a different setup. In a threshold signature scheme, a setup will give you a verification key. And then at any point in time to sign a message, any t out of those n, it could be different t for different messages, but as long as t out of n parties participate in a signing protocol, the resulting signature is verifiable with respect to the verification key that the setup algorithm gave you. Sorry, that was a mouthful. Yeah.
To put it very briefly.
But what I said does not talk about weights, which is why we had to invent something new. We needed to deal with weights. Yeah.
And Joseph? To put it very briefly, the T of n, yes, the length of the signature is the same regardless of what your T of n is.
Yeah.
Amazing. All right, so a little lighthearted comment from Nick that I do want to show here. So in the diagram, you substituted Carol for Charlie. So, our community did pick up on that. Carol was on a day off. So
thanks for keeping me honest. Yeah.
All right, so another question from one of our viewers. Is the same TSS infrastructure planned for other Hedera services like HTS messages, scheduled transactions, smart contracts, or is it scoped to ledger state signing for now?
I'll address this one, Rohit. So TSS is being used to sign the block, not the state. So when we sign the block, we're actually signing all of the inputs to the block, all of the outputs from the block, and the event structure that generated the block. So you get a single signature that proves the events and the Hashgraph algorithm and the transactions and the execution of those transactions, including all of your HTS messages, all of your schedules, all of your smart contracts, including your smart contract logs. So everything's in the block and all of that is signed in one shot.
Excellent.
So when we turn this on, it'll cover all of those things.
Thank you, Joseph. Great question and great clarification. I do want to go back to a question that came from Munif around Clipper. So somewhat related, but certainly a different topic. How can we participate in Clipper beta testing? And so right now, you can go to hashgraph.com/CLPR or /Clipper, and there you're going to find more information about the current state and the beta state for Clipper. But I also do want to open it to Rohit and Joseph, if there are any thoughts around the interaction between TSS, Blockstream, Blocknotes, and Clipper, if there are any thoughts around, how those things come together, if at all.
They absolutely do, in that TSS makes Clipper possible. So by adding TSS and the signature on the block, the way we've structured it, and the structure of the block tree, the Merkle tree that represents the block when you sign it. That's critical because it allows us to prove state, because state is one of the subtrees within that giant block Merkle structure. So at any block boundary, at the end of any block, we can actually prove the content of state for any item. In fact, we can also go back to any previous block and prove state for that block as well. So we can provide these state proofs. They're very efficient and very small and very easily verified. And they're verifiable forever because you have this forever verification characteristic of wraps plus TSS. So because we have hints, because we have TSS, because we have wraps, because of this brilliant mathematical work that's been done, we can actually prove state very effectively, very efficiently. So we can transfer those proofs across the network between um, any given two networks of different types and have the verification be efficient, even in something like a smart contract. So TSS absolutely makes Clipper possible.
Amazing. Thank you for that insight, Joseph. And just for the viewers that may not be familiar with Clipper, earlier this month at HederaCon, Clipper was introduced by Hashgraph. This is a new bridgeless cross-ledger protocol that enables that secure communication and token transfer between independent blockchain networks. So certainly something that is enabled by this TSS development that you're hearing about today. So thank you for that, Joseph. Let's see if there are any other questions coming in from the audience. All right, so it looks like that is all that's coming in. I did get a question ahead of time, Rohit, and you did lay out the different requirements. I think it was 6 requirements for the threshold state signing. You mentioned the fixed verification key, and that sounds like a complex thing to pin down. And so, why can you walk us through why standard threshold signing breaks in this part?
Yeah, that's a really good question. So I think, if I'm being honest, there are ways to use threshold BLS schemes from literature, where let's say that which has a threshold access structure, let's say T out of n, and let's say you add an n+1th node, and there are protocols that where the parties in the older committee they exchange messages, and then everyone in the new committee has a new set of key material, allowing the verification key to be fixed. Yes, we know how to do it, but as soon as you add weights to the mix, that breaks down. Because as an example, let's say I have a weight of 499, you have a weight of 501. Now we're going to need like all 501 amount of cryptographic key material, just as an example. So once so the reason that became challenging is supporting both weights and network evolution, which is why we had to invent a new algorithm called hints. But we don't know how to do this. What I described, we still don't know as a cryptography community how to do this with a fixed verification key. Hence the reason to build all this additional wraps math. Yeah. But if hints did support that feature, sure, we didn't need to develop anything else. Yeah.
Understood. All right. And then I do want to go back to one point that you both mentioned around the fact that you only need one honest participant for this thing to be successful. And so can you help us understand in plain language, how did you verify that each participant did their part honestly?
Yeah, so honesty has 2 components here. One is that you're not holding on to the secret randomness that you use for participating. So the attack, the ceremony breaks down if all of the, let's say the 40 people who participate, if all 40 of them hung on to the secret values. And the way it's also non-trivial to do that, like you'll have to inspect the memory during the ceremony and grab those values. It's not easy to carry out either, but it's possible. But if all 40 of them did that, then they could come together and have the ability to forge invalid proofs and completely compromise security. But as long as one of them didn't do that, then we have security, which is why we feel very confident. But to answer your question, what it exactly means, to be honest, yeah, one is like not doing the attack that I just mentioned. The other is not ignoring the following the protocol. And the protocol says Carol or Charlie, they take Bob's output and then they produce the next output for Dave. they did not skip over Bob. They did not, like, for example, use Alice's. That's another key component of this, and that's what the two come together implies honesty. And as long as one person did that, we have security. Yeah.
Makes sense. And I would add that with the mature governance that we have with the council members participating in this process, also with the community projects that contributed to this, it seems like it was a bar that was comfortably met to have those honest participants.
Yeah. So just before, so I think perhaps I didn't answer the question. So yeah, we actually have these lightweight zero knowledge proofs that, for example, Carol, they did take Bob's output. So there's actually a proof that Carol computes, and it's a very lightweight proof. And we have a transcript of the whole protocol, and anyone in the world can look at the transcript and check those properties do indeed hold true. Yeah, mathematically.
That's awesome. That's awesome. All right. One more question here from Dave Proxy 80. Are you looking at using lattice-based or hash-based cryptography for the post-quantum secure Hedera?
Great question. Yes to both. Yeah. Early days, but yeah, we're looking at all those options.
All right, Dave, there you have it. And then the last question that I see here is, when you mention votes, Nick is asking perhaps for a clarification. When you say weights, do you mean weights for virtual voting?
So I think the virtual voting comes from the consensus algorithm. Joseph can probably answer this better, but we do have a corresponding set of weights that we use for TSS only. The two are related, and Joseph can highlight that. But when we said weights, we meant for the TSS signing. Yeah. And so the property is that half of the network by weight has signed off on the block. Yeah. Sorry, Joseph.
Yeah, I was going to say, so the weights for consensus are slightly different from the weights for TSS. They're both based on stake, and they're both equivalent, but they're not identical.
Very important clarification. Thank you for that, Joseph, and thank you for asking for that information, Nick. All right, folks, we're at the end of the questions and of the session. Remember, this was live streamed to multiple channels. This is also going to be available as a recording, so you can always go back, watch it at your own convenience, or restudy the segments that you're most interested in. Certainly a lot of valuable and interesting information that we got from Rohit and Joseph today. And guys, I do want to thank you for spending your time with us, giving us this information, and having this transparency about the TSS ceremony that took place over the last few weeks, or April 15th to April 28th. With that, let's have a great rest of the week, and looking forward to having you again at some point in the future in these community calls. So thank you, Rohit. Thank you, Joseph.
Thank you.
A clip